Concepts and definitions in control engineering.
A system is a collection of interacting elements, and when its variables change with time, we call it a dynamical system. To study such systems, we use mathematical models expressed as equations. We describe systems through variables: inputs, which may be controllable or noisy; outputs, which can be measured or define performance; and state variables, which capture the full condition of the system. Systems can be classified in many ways: analog or digital, continuous or discrete, time invariant or time varying, linear or nonlinear. Interestingly, very different physical systems can share the same mathematical form. These are called analogous systems, such as the spring-mass damper in mechanics and the RLC circuit in electronics. Together, these ideas form the foundation for analyzing and designing complex systems across science and engineering. Let's begin with the idea of a system. A system is simply any collection of interacting elements where the variables are connected through cause and effect relationships. In other words, when one part changes, it influences the others. Now, when those variables depend on time, we call it a dynamical system. This means the system evolves, step by step, as time moves forward. Finally, to study and predict the behavior of such systems, we often use a mathematical model. This is a description of the system expressed in terms of mathematical equations, allowing us to analyze, simulate, and understand its behavior more precisely. Now let's talk about system variables. These are the quantities we use to describe and analyze how a system behaves. First, we have input variables. Among them are control inputs. These are the manipulative variables, usually known and computed precisely. On the other hand, there are noise inputs. These are non-manipulative, often unknown, and can disturb the system's behavior. Next, we consider output variables. These come in two forms. Sensor outputs are the variables we can directly measure with sensors. Performance outputs, however, are the variables that actually govern how well the system performs. Keep in mind, sensor outputs and performance outputs may or may not be the same. Finally, we have state variables. This is a special set of variables that describe the system completely. We'll study these in more detail later, but for now, think of them as the internal memory of the system that captures its full condition at any given time. Systems can be classified in different ways, depending on their properties. At the highest level, we distinguish between analog systems and digital systems. Analog systems deal with continuous signals, while digital systems work with discrete signals. But beyond that, both types of systems can be further categorized using the same criteria. For example, a system may be a lumped parameter system, where variables are concentrated at distinct points, or a distributed parameter system, where variables spread continuously across space. It may operate in continuous time or in discrete time. Another distinction is between non-quantized and quantized systems, which reflects whether variables take on continuous values or step-like, discrete values. We also classify systems as time invariant, meaning their behavior does not change with time, or time varying, where the rules evolve over time. Finally, systems can be linear, where outputs scale proportionally with inputs, or nonlinear, where the relationships are more complex and often harder to predict. These classifications give us a structured way to analyze and design systems, whether they are analog or digital in nature. Sometimes, very different physical systems can actually share the same mathematical structure. We call these analogous systems. That means the equations describing their behavior have the same form. even though the variables may represent different physical quantities, and the parameters may take on different numerical values. For example, a spring, mass, damper system in mechanics, and an RLC circuit in electrical engineering are mathematically analogous. The motion of the mass and the oscillations of the circuit follow the same type of equations, even though one deals with forces and displacements, while the other deals with voltages and currents. We truly appreciate your subscription and support.